Okay, so we're doing number 5 on the buffer review problems. So it tells you that you have a buffer solution. So they ask you 3 different questions. The first question they ask is, what is the pH of the buffer solution? And so please understand that when you make the buffer solution, you're just mixing the weak acid with the conjugate base, and you haven't done any neutralization yet. Neutralization will come when you add a strong acid or a strong base to the buffer. So if it's just asking for the pH of the buffer, then you just start with the buffer equation. The hydrogen concentration is equal to the Ka times the acid over the base. And then they give you the Ka is 6.8 times 10 to the negative 4th. And the acid is hydrofluoric acid, and they tell you that it's 0.11 molar. And it tells you that the whole buffer solution is 200 milliliters. So you don't have to worry about the concentration changing. You don't have to calculate moles or millimoles, so you can go right with the molarity. It's easiest to use. So I'm just going to plug in 0.11 molarity for the acid, and it said the base, the sodium fluoride, is 0.1 molar. So again, the HF is the acid, and it tells you the molarity directly, and the sodium fluoride has fluoride in it, and that's the conjugate base, and it tells you the molarity of that, and you're not combining any volumes, so you're good to just put the molarity directly into the equation. So this simplifies to 7.48 times 10 to the negative 4th. So again, because that's the hydrogen concentration, we're just going to negative log that, and that will give us our pH. So the pH works out to be 3.13. And because it's a weak acid with a Ka value that's around 10 to the negative 4, that makes sense that the pH is that value. Okay, so now we're going to continue this problem, and the next thing that we're going to do is we're going to add 0.015 moles of nitric acid. So what you need to realize here is nitric acid is a strong acid. So again, remember in your buffer you have H plus molecules and F minus ions. So when you add the strong to the buffer, you have to make a decision and select which thing is being neutralized by the strong thing that you're adding. So because we're adding strong acid, I'm going to show a neutralization equation. I'm going to show H for the strong acid H ions. And then I go and I think, is the H going to neutralize HF? That doesn't make sense because that's a strong acid with a weak acid. So is the H plus going to neutralize the F minus? That makes sense because the F minus is a base, and in the water is forming hydroxide ions. So the H plus is able to neutralize the F minus conjugate base ion. And again, remember, when you neutralize a strong acid with a weak base, water won't be in the net ionic equation, so they're just going to come together to make HF. What we do need to remember with this problem is it is a buffer. So there is going to be some initial F minus and HF in the sample before you add the H plus. So we have to consider everything that's there. So because you're adding just moles of HNO3, you could deal in moles, but because they give you the buffer solution in molarity in milliliters, it might make more sense to use millimoles. So them telling me that there's 0.015 moles, there is 1,000 millimoles in 1 mole. So if this is moles and I want to deal with millimoles, I'm just going to multiply by 1,000. So that gives me 15 millimoles of the strong acid. So there's 15 millimoles of the H plus. And then the F minus is in 200 milliliters in the buffer. And again, from the beginning problem, they told me it was 0.1 molar. So I'm going to take 0.1 molar for the F minus and multiply by 200 milliliters. And that gives me 20 millimoles of the conjugate base ion. And the HF, again, is in the buffer originally, and its molarity they give me from the beginning is 0.11 molar. So I'm going to multiply that by 200 milliliters. So understand that both the F minus and the HF are in that 200 milliliters together as they are in the buffer mixture. And that gives me 22 millimoles of the HF. So then I just evaluate it to see the limiting reactant. So for every one of these, I need one of these to make one of those. So if I have 15 of these and 20 of these, this is my limiting reactant, and I'm going to have excess conjugate base ion. So as this goes forward, this is going to go down 15 millimoles. So you have no hydrogen ions left over. This is going to go down 15 millimoles. So we have an excess of 5 millimoles of the F minus. And as it goes forward, this is going to go up 15 millimoles. And so we have 37 millimoles of the HF that is produced. And then you look at it and you say, okay, is this a buffer? So because we have excess weak base and acid that was there and more formed, because you have both of them together, that is a buffer mixture. And again, when you realize it's a buffer mixture, you just go right to the buffer equation. The H concentration equals the Ka times the acid over the base. And so the H concentration is going to equal the Ka that I used earlier is the same one. However, we can keep going. So even though it neutralized the base here, it still has both HF and F minus. So we can use the same setup. So the Ka is 6.8 times 10 to the negative fourth. And again, the acid is HF, so that's the 37 millimoles. And the base is the F minus, so that's 5 millimoles. So that simplifies to a concentration of 0.005032 molarity. And the pH is going to be the negative log of that. So that gives us a pH of 2.30. So if you go back and just think if that makes sense, the pH of just the buffer originally was 3.13, and we're adding strong base, so the pH should go down, but not a significant value. So it's going down to 2.30, which seems about right. So we're going to do one more part to this problem, where we're going to take the original buffer and now add a strong base. So if we're adding a strong base, then we're going to show hydroxide ions from the strong base. And again, we're just going back to the original buffer. So you have to select and choose which one the OH is going to neutralize. So the original buffer has HF and F minus, and because OH is a strong base, it's going to neutralize the acid that's in the buffer. So we're going to select the HF to use in our neutralization equation. So OH plus HF makes water and the conjugate base ion F minus. So they give me the OH as a concentration with molarity. So what I'm going to do is find the millimoles of that. So if the OH is 0.01 molar and there's 25 milliliters, that gives us 0.25 millimoles. And the HF is 0.110 molar from the original solution, and there's 200 milliliters of it. So that gives us 22 millimoles of the HF. We don't worry about water. The F minus in the original buffer solution is 0.1 molar, and there's 200 milliliters. So that gives us 20 millimoles. So again, it reacts in a 1:1:1 ratio, and because the concentration of our NaOH is significantly smaller than the other ones, we really are only adding a small amount compared to the other values, just the 0.25 millimoles. So this is going to be our limiting reactant. So this is going to go down 0.25 millimoles, and you have no excess hydroxide ions. And this is also going to go down 0.25 millimoles. And I'm just going to keep those extra digits, even though we might be unsure about maybe the last one, and say that this is 21.75 millimoles. And as it goes forward, this goes up 0.25 millimoles. And so this gives us 20.25 millimoles of the fluoride ion. And again, we look at what we have and we ask ourselves if it's a buffer. So because I have excess weak acid that hasn't all reacted and conjugate base ions that are still there, we have a buffer. So we just go ahead to our buffer equation and we set up H concentration is equal to Ka times the acid over the base. So again, the Ka is 6.8 times 10 to the negative fourth. The acid is the HF, so we're going to use the 21.75 millimoles. And the F minus is the conjugate base, so we're going to use 20.25 millimoles. And this simplifies to 7.3 times 10 to the negative fourth. And again, if we negative log that, we'll get the pH. And so we get a pH of 3.14. And again, you want to make sure that that makes sense. So if we go back to our original buffer again, our original buffer that we made was 3.13 pH. And then in this problem, we're adding a strong base, but a relative smaller amount compared to the rest of the buffer. So pH is going up a little bit, but not a lot. And so that number would make sense. Okay, thank you.